Today, we're going to take a look at one of Calc 1's greatest hits style of problem, and that is to find the dimensions of a cylinder that has a fixed volume where we want to minimize the surface area. So we're going to fix the volume of our cylinder at 40 cubic centimeters and find out how small we can make the surface area. All right, so let's go over the facts that we have in evidence. The volume of a cylinder is pi r squared times h. This we get by taking the cross-sectional area and multiplying it by the height. This is the same as when we find the area of a rectangular solid by taking length times width and multiplying that by the height. Length times width is the cross-sectional area of the rectangular solid. We multiply the area by the height. So our volume calculation is pi r squared, the area of a circle, multiplied by the height. Because that's how we find the volume of an object with a fixed cross-sectional area. In the surface area calculation, we have the side of the can and then the top and the bottom. The top and the bottom of the can are circles. So the 2 pi r squared it's going to be the area of the top and the bottom, because the top and the bottom are just two circles. The 2 pi r h is the side of the can. So the side of the can or the cylinder is a rectangle where the length is the circumference of the circle on the top. The length is the circumference. So if we imagine taking this cylinder, slicing it from top to bottom and unrolling the sides, we still have a height, and we unroll, and the unrolled length will be the circumference of the circle. So we have a volume of pi r squared times h. That's just the area of the circle multiplied by the height. Area is going to be in square centimeters, the height's in centimeters, so we'll get a volume in cubic centimeters. For the surface area, I have 2 pi r squared representing the two circles, the area of the two circles on the top and the bottom. The radius is measured in centimeters. Radius squared will give us square centimeters. So this term gives us square centimeters. Over here in the first term, the radius is in centimeters and the height is in centimeters. Centimeters times centimeters gives us square centimeters. So we got square centimeters for the surface area. Any questions?
Yes, Professor Rich. Thanks for drawing. So if I look at the draw, h is the height and 2 pi r is the length, isn't it?
Yes.
Wow, okay, I see it now, thanks.
So if we imagine, so once again, if we imagine this length on top, I'll highlight it in purple. If we take this side and wrap it around the circle on top, that will go around the top of the circle of the cylinder right here. So it's 2 pi r is the circumference of the circle around the top. All right. Let's think about what we want to do. We have two quantities, a volume and a surface area. The way that we're going to play this game, this is going to be a game that we call constrained optimization. I want to find the minimum surface area subject to some constraint. Our volume has to be fixed at 40. If I just said find a cylinder with minimum surface area, make the radius and height 0, and the volume and the surface area will be 0. But then the volume would also be 0, and that's not helpful. So what we want to do is we want to minimize the surface area subject to a constraint that is fixed volume. So we want to minimize, our goal is to minimize S equals 2 pi RH plus 2 pi R squared, subject to pi R squared H is equal to 40. So we have an objective function and a constraint function. So here is our constraint. And the other function is our objective. So where it says that we want to minimize the surface area, we need to solve S prime equals 0. So we want to minimize our objective function. And to find a minimum of a function, we want to solve S prime equals 0. But S is a function of radius and height. S is a function of R and H. And this is only calc 1, which means we only get to use one variable, not two variables. So it's a big restriction when we only get to use one variable. It makes the calculus portion easier, but we have to do a lot of more work at the front end to make sure that we only have one variable. So we want to solve, take the derivative, set it equal to 0 and solve, but our function S involves radius and height. So I need to write S so that it only involves one variable. We want this to be in terms of one variable. So we want S as a function of one variable. We want S as a function of one variable. So that we can find the derivative. And that's where the constraint comes in. What we're going to do is we're going to use the constraint, which establishes a relationship between R and H, and then use that to eliminate R or H from our objective, so that our objective will involve only one variable. So let's use the constraint. And it looks like it's going to be easiest to solve for H. If I solve for R, I'd have to take a square root. Everything's positive here, so that might be okay. But then we're involving square roots. If I solve for H, I'll just get 40 over pi R squared. So what we're going to do is we're going to use the constraint to solve for one of the variables. So I'm going to take the constraint and I'm going to solve for H. Now I'm going to use this relationship between R and H in the objective so that the surface area will be a function of one variable. So now I'm going to take my surface area, and it's going to be 2 pi times R times H, which is going to be 40 over pi R squared.
Professor,
Yeah.
can you explain the algebra behind how you got 40 over pi r squared?
If 40 pi r squared, or sorry, if pi r squared h equals 40, just divide by pi r squared. Because it's
Why wouldn't you necessarily just add it?
Because it's not included with addition or subtraction, it's multiplied. If I have 5h equals 40, then h is equal to 40 divided by 5. And that's what we have. Pi r squared is being multiplied by h, so I have to divide to get h by itself.
Oh, okay.
So we take our constraints, solve for one of the variables, and plug it into our objective. Now notice that our objective only involves r. Now our objective is of one variable. And that's what we wanted. We want the s to be a function of one variable. I want to simplify this function because this is what we're going to take the derivative of. So I'm going to cancel out a pi here and cancel out one of the r's. So s as a function of r, see, I still have 2 times 40 is 80. The pi's cancel out. R divided by r squared will leave an r in the denominator. And nothing happened over here. So now we've got s as a function of one variable. Now that our objective is only one variable, I'm going to write this as 80r to the minus 1 plus 2 pi r squared, because the next step is to take the derivative, set it equal to 0, and solve. And when we're taking derivatives, if we can write powers of the of r, then we should write powers of r. So s prime is going to be negative 80r to the negative 2 plus 4 pi r to the first. Take the derivative, and the next step is to set it equal to 0 and then solve. But here's our derivative. Once we have the derivative, we set the derivative equal to 0 and then solve. In this case, we'll solve for r. Once we have r, we can go back and find h. Any questions up to this point?
Why don't we use the product rule to get the derivative of 2 pi r squared?
Pi is constant. Pi is not a variable.
Okay, thank you.
So let's flip the page and set this derivative equal to 0 and solve.
Professor Leach, could I stop one moment, please? On the minimize, and then you put the arrow down.
Yeah.
You mentioned like s is a function of r and h. So every time, so this is the volume equation. Is that
no?
correct?
That's the surface area. S is the surface area.
So every time we see the surface there, it represents the r and the h2 function. And on the right, you wrote down subject is substring pi r squared multiple h equal 40. That is the volume, right? I'm looking.
That's the volume.
Oh, so you set the volume to h to get it to one variable. Got it. Thanks.
Yeah. So let's take the s prime, set it equal to 0, and solve. So I'll have, let's see, negative 80 over r squared plus 4 pi times r equals 0. So now we're going to solve s prime equals 0. So since we have opposite signs, we can solve however we want. We can multiply through by r squared, but I think what would be easiest is to just add the 80 over r squared to both sides and then multiply by r squared. So 4 pi r cubed is equal to 80. And so now we can solve for r just by dividing and then taking the cube root. So r is equal to, let's see, first I would divide by 4 pi. So 80 divided by 4 pi. And then we would take the cube root of this. I guess I could simplify the 80 and the 4 to get the exact value. So I could write this as the cube roots. 80 divided by 4 is 20. So the radius is the cube root of 20 over pi. I'm going to get an approximation just so to see if anything makes sense. So I want the cube roots of 20 divided by pi. Let's just go to the 1/3 power. And 1.853. Let's do 5 significant figures because I almost always pick 5. This is a radius, so it's going to be measured in centimeters. Next, we would need to use the fact that h is 40 over pi r squared to calculate the height. So h is 40 over pi r squared. So that'll be 40 over pi times, now I definitely want to use the approximation, 1.8534 squared. So I'm going to grab my calculator and do 40 divided by pi times answer squared. Got to make sure you put parentheses because your calculator knows the order of operations. And if you ask it for 40 divided by pi times the square of the answer, it'll divide by pi and then multiply by the square of the answer. And I want 40 to be divided by. I want pi times the square of the answer to go first, then 40 divided by the result. So it looks like the height of the can should be 3.7067. So it looks like we should make a can with a where the dimensions of the can, it looks like will contain 40 cubic centimeters with a minimum surface area if we make the radius 1.8534 centimeters and the height 3.7067 centimeters. One thing to note is that we didn't check to see if this is going to be a minimum or a maximum. That's a little bit, that was a little bit meta of us thinking, stepping outside of the problem, knowing that this is a problem. We only got one critical point, and there's something that should be telling us that this critical point is going to be a minimum and not a maximum. One way we could find this out, I suppose, is to look at the graph of our surface area function when it's written in terms of r. If we're going to look at the graph, then we shouldn't bother taking the derivative because we'll just look at the graph. So let's go to our graphing calculator and check things out just to clarify. So let's share screen for Desmos. And our function is going to be Let's see. Let's take a look at, we had 80 over r plus 2 pi r squared. So I'll have 80 over r plus 2 pi r squared. So right now we don't see anything, but if we zoom out, aha, there it is. It's not really useful looking at these negatives over here. Let's see. So there's our minimum R, 1.853, and that's what we got. Like I said, once we bring technology to bear on a problem, we should just kind of use that. But finding the dimensions for the minimum surface area was not the big goal of the problem. The goal of the problem is to think about what we want to do and what we need to do to get that. We want to take the derivative, set it equal to 0 and solve, but our function involves two variables, r and h. Fortunately for our heroes, we had a separate equation involving r and h where we could eliminate one of those variables.
Professor Lich, could I ask where did you get y equal 80 over x? Where is that coming from?
That was our objective function. That was our objective function once we eliminated the h variable. Desmos doesn't like s and r, at least it used to, not like s and r.
And then the plus 2 pi x squared, where is that coming from?
2 pi x squared.
Oh, okay. Could I repeat this one? Thanks, Professor Lich. So every time I see this formula, this is the surface. So there is the h and the r. So I can set the function. When I look for the r, I can set the function to derivative, and then I can set the volume formula for the h, and then I can plug back to the r.
That wasn't the order that we did things.
Yes, yeah, I see.
We set up our objective function.
Mhm.
Our constraint involved was a relationship between the two variables in our objective function.
And that's for the h. We're looking for the h.
Yeah, that's why we use the constraints. We use the constraint to eliminate the h from our objective function, so that our objective function was in terms of one variable.
Yes, I see the note here. Thanks, Professor Lich.
If I give you a function of two variables, y'all don't know how to take the derivative yet. So we need to break things down. We need to simplify things into a function of one variable.
And then set up the function to derivative and then plug everything.
Then take the derivative,
Got
set
it.
it equal to 0,
Very
and
clear.
solve.
Thanks, Professor Lich. Very helpful. Thanks.
So we didn't verify this. We could see by the graph that this is going to produce a local minimum. We could also, since we have S prime, if we're concerned, S prime was negative 80 r to the negative 2 plus 4 pi r to the first. If we take the second derivative, S double prime, we'll get positive 160 r to the negative 3 plus 4 pi. Now we can see, since r is positive, if we plug a positive number into this expression, S double prime is going to be positive. Therefore, S is concave up for R positive. Therefore, we have a local minimum . I've been saying when, so when R is 1.8534.
Professor Lich, could I ask a quick question on the S double prime second derivative?
Uh-huh.
we have 160 r to the power negative 3 plus 4 pi r. Where's that r going? We have 4 pi.
It's r to the first. The derivative of r to the first is constant. We do 1 times 4 pi, and then it's r to the 0 power.
So the r will be disappear. Is that what you mean?
The derivative of a constant is, the derivative of r is 1. It's not just disappearing. The derivative of r is 1. Right? The derivative
Oh,
of x is equal to 1.
and the pi is still there. Okay, well, I'll look at it again. Thanks, Professor Lee. So the r is 1. Got it, thank you.
CU stands for concave up. Since the second derivative is positive, the function is concave up. So question is to look at the graph. If we look at the graph of the function, it looks like Desmos will accept S and R, and it will figure out which one is vertical and which one is horizontal. So if I look at the graph of the S, once I got S down to one variable, once S was just 80 over R plus 2 pi R squared, if I look at the graph of that function, this is our objective function once it's in terms of one variable. Then we could look for where we have a minimum. So everything over here on, notice that over there on the left, that's where R is below 0. And we don't care if R is below 0. We can't have a negative radius for our cylinder. So we're concerned with what's going on when R is positive. And so we're looking for this spot right here, where we have a local minimum. And that happens at 1.853, which is the value that we got for R. Any other questions? So what we want to remember is that if I want you to find a maximum or a minimum, I want you to optimize a function. That function is called the objective function. To optimize a function, we take the derivative, set it equal to 0, and solve. If our function involves two variables, we'll need some other information, because right now we're only allowed to find derivatives when we have one variable. We're not allowed to use two variables. So in this problem, the volume provided a relationship between the two variables in our objective function. So that's how we were able to eliminate one of the variables.
Professor?
Yeah.
Did I hear earlier that you said you could use S prime to calculate the radius?
That's what we did. We found
Yeah,
S prime
don't-
and set it equal to 0 to solve.
Yeah, I don't understand why it's the radius though.
That's the variable that's in S prime. So what we're doing is we're taking S prime.
Oh, because you use that. Oh.
I wrote
I
S
get it.
in terms
Okay.
of the radius. And so S prime was also a function of the radius. So that's why it's the radius that comes out. That's going to be where our local minimum is.
Okay, that makes sense. Thank you.
Cool. Any other questions?
Yes, Professor, it's a quick question on the very bottom. So the S prime, basically we're looking for the critical point, isn't it? You show in the decimal earlier. Am I right?
Yeah, we were looking for the critical points.
And the S double prime, we're looking for is that inflection point or something you mentioned earlier? I forgot.
In this case,
Mhm.
we're going to use the second derivative to determine whether a function is concave up or concave
Right.
down at a point. Because if the function is concave up
Got
at a
it.
critical point, then we have a local minimum.
I got it. Thanks, Professor.
All right. This is a classic problem of calculus to find the minimum surface area for a fixed volume in a cylinder. One thing to note is that the height is like 3.7 and the radius is 1.85. So the diameter is about 3.7 as well. If you're trying to minimize your surface area for a fixed volume, you want things to be as spherical as possible. In this case, we couldn't make a sphere because we had to make a cylinder. That was one of our restrictions. But in general, if you're trying to minimize your surface area and contain a volume efficiently, you want to use a sphere. That's to reduce the amount of material. Now, this is not a practical solution because it would be ridiculous to ship liquids in cylindrical containers, because then there's going to be all kinds of wasted space when you pack the spheres. But if you just got one sphere and you need to minimize your surface area, you should make if you just have one container and you want to minimize the surface area for a fixed volume and it doesn't matter what shape you're using, just use a sphere. The Death Star is an efficient use of the exterior material. The board cube is not, although they did try because they made it a cube instead of a sphere. Spheres are great for material use, but also terrible to live in because there's all kinds of unusable space down in the corners. Not that a sphere has corners, but you know what I mean. Like if you build a hemisphere, like a dome, and you had to live in that, you wouldn't really be able to go up to the walls because it like gets too short. You know what I mean? Anyway, just wanted to point out that a radius of 1.85 is a diameter of about 3.7. So we're trying to square off this can as much, a diameter of 3.7. So we're trying to square this off as much as possible, 3.7 by 3.7. All right, that's our problem for the day. The tricky parts is coming up with our objective and our constraints. A lot of times in math classes, a common refrain is to say, well, once the problem is set up for me, I can do the problem easily. It's setting up the problem that's the difficult part. Setting up the problem is the point of the problem. Working out the details, that's secondary. The point of doing math is to not solve problems that are set up for us already. Because those problems, if they're set up for us already, they've been solved already. The trick is setting up the problem. The trick is asking the right question. That's why I say when you graduate, you need to have more questions than when you matriculated. If you finish college and you don't have more questions than when you started college, you did something horribly wrong. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.